Today I want to talk about the different signals, in particular the clock and the control signals, and how they need to interrelate with each other. The whole point here is preparing for how we're going to construct our control signals such that we can control everything in a timely manner without having one particular signal be timed incorrectly and extending into the wrong part of a clock cycle.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
So here we've got the clock signal. Obviously, this is going to be generated by my clock circuitry. I need to invert that clock as well. What I really need to be able to demonstrate is that those two signals are as symmetric as possible. I want to have almost no delay, and if I can get absolutely zero delay in that clock cycle versus the inverted clock cycle, that's going to be ideal. What I want to be able to do is manufacture the delays I need in the actual control signals themselves and not have to rely on an inverter to provide a delay to an inverted clock signal. Now, for display purposes on an LED, that's fine, but for controlling the CPU, I'm really striving to have much tighter tolerances. My typical control signal is going to generally be low when the signal is not asserted, and then go high during the clock cycle in which it is required, and then return back to low when it is not required. And the reason I want to do this is equivalent to having bits in an EEPROM, if you will. I'm hoping to try to find something a little bit better to control the microcode or the control word. But when something is high, I want it to be producing the signal, and when something in the control word is low, I want it to be quiescing or not producing that signal. So this indicates here as the signal comes in, it's going to go high. It's going to stay high for the entire clock cycle in which it is intended, and then it's going to return back down to low at the end. This is the data coming off the control word, not the signal that's being generated out onto the buses, or to the control lines, I should say. One thing I want to call your attention to is I actually have thickened the part of the line that is of interest to us, specifically what we want to see happen or where we want to see things happen. And so this could be the rising edge, it could be the high edge, it could be the falling edge. We really don't want anything to happen on the low edge of these control signals from the control word. And I want to make sure that I'm trying to be very clear about this. This is specifically related to the control word, not the actual signal traveling to the register, module, what have you. For the fetch instruction for the fetch register and the instruction register, both of those need to be able to latch their values. For our purposes, I want those values to be latched on the rising edge. And so this ends up being a complete copy of the clock cycle. So if I compare this to what the clock looks like, the resulting signal that I want is the clock cycle. So there's no manipulation, nothing fancy I need to do with this in particular. I don't need to and it or it do anything like that. And as a matter of fact, there's absolutely no delay in the clock signal, which is advantageous to us, because what that does is that gives me the ability to latch the instruction register or the fetch register slightly before any of the other control signals go out. So it gives it an opportunity for that to settle down a little bit. And that is really good. Now, I also have a control word that I'm going to be latching so that I actually can reduce some of the latency and make sure that it is available through the entire clock cycle. And so that control word is going to be, again, a complete copy of the clock signal. And so as a matter of fact, the control word latch and the instruction and fetch register latches are all going to be driven specifically from the clock signal. Now I have an AND latch signal, and these are going to go off to registers, but may end up going off to other modules as well. And this AND latch signal is a little bit different. We want to frame that such that the signal is high most of the time and then comes low right before it returns back high. And it's that rising edge that is going to be of interest to us. And then once it's been returned back to a high state, it's going to stay at that high state until it is required again. And so this is where we actually need to combine some signals. So this, if you take the control signal and then look at it next to the inverted clock signal, if I use a NAND gate, when both of those signals are high, my AND latch signal will drop low. And then when that's done, it's going to return back high, giving me that latch activity that happens at the end of the clock cycle, the last thing that takes place. The bus asserts, again, we want to have happen for the entire clock cycle, but the native signal on the register or any of the 74HC541 line drivers is when that signal goes low, there is an assert. So what we really want to be able to do is hold that high when we're not asserting and then bring it low when we do want to assert. And if we look at that in conjunction with the control signal, that's just an inversion of that control signal. Now, there will be 74HC138 demultiplexer that's involved in that, which actually does the inversion for you naturally. So that will take care of the inversion for me just the way I need it to. And then finally, the load increment decrement. These are going to be two signals, and that's why I've got the actual clock pulse or the signal being dotted, because it could either remain low for any of those two given lines, or it can go high. So 0, 0 again being do nothing, both of those signals would remain low. And if I take that signal and AND it with the inverted clock, then on the second half of the duty cycle of the inverted clock, that signal would go high if the signal was a 1, but both being zeros, that remains low. So for 0, 0 being do nothing, that signal remains low, which is exactly what we want it to be. For 0, 1, the most significant bit remains low, the least significant bit goes high on the second half. And what that does is it also frames that signal such that it is in the native form the register is looking for, meaning that the increment happens halfway through the duty cycle of the clock. Again, increment would be 1, 0, same type of situation. Decrement 1, 1, both signals would go high at the same time. Now on this chart, what I have here is how I plan on wiring these up. So I've got a 74HC138 that sits on the control module. And what it shows up at the top is that there's a 45 nanosecond delay in presenting that signal from its input to any of its outputs. When I add a clock signal in to enable or disable that particular IC, there's an 8 nanosecond penalty that I pay for that. So it's either 45 if I'm using it just outright and it's always presenting signals, or it's an additional 8 nanoseconds if I have to enable disable that particular IC to get the signal out. So for example, the latch, I can take care of that by pushing the clock into that particular IC to enable disable the output. I end up with an extra 8 nanosecond penalty for that, but then I need to buffer the output to get it in line with all the other signals. And so that's what I've got over here is my total propagation delay. I have zeros up here for some of these, meaning if they are exactly on time, and then I've got 70 or 78 nanoseconds over here for some of these other signals, indicating exactly what the timing of those are going to be. So if I needed to NAND a couple of signals together to get the right output, there's a 25 nanosecond delay on that. If I was to use a straight up inverter to the 74HC04, there's a 24 nanosecond delay that gets added. If I was to use an AND gate to AND a couple of signals together, just like I did with the load increment decrement, there's a 25 nanosecond delay. And if I was to use an XOR gate as either a buffer or an inverter, there's a 25 nanosecond delay that gets added onto that. Now, the register modules also have a 74HC138 built onto the board. It's got a 45 nanosecond delay associated with it. It is not wired up such that it uses the clock or any other signal to enable disable the IC, so there's just a simple 45 nanosecond delay. And the load increment decrement is handled by that particular IC. So that's a 45 nanosecond delay. Added to that the required 25 nanoseconds in order to AND those signals together. That gives me the 70 nanosecond delay that I'm looking at for that particular signal. The bus assert is exactly the same. It's handled by the control and is not enabled by a clock pulse, so it will constantly be outputting, and so that would be a 70 nanosecond delay. And then I've got, for example, the AND latch, which is also going to be multiplexed in the control word, so it has to be demultiplexed by a 138. This one's going to be clock enabled, so I pay a 78 nanosecond penalty for that. Well, let's call that a delay rather than a penalty. Okay, I have the instruction register pulled away from the rest of the computer. And what I've done is I've added this extra breadboard on the end up here. Now, full disclosure here, I did make an attempt to put this together and realized that the power rails were just too congested. So I doubled up the power rail here and I deleted that footage and I'm going to redo it here. I might end up doing it a little bit differently than I did before. Let's start with the 74 LS86. This is going to be a quad 2-input exclusive OR. And then to that, I'm going to add power and ground. And then this is the clock signal that comes directly from the clock module. And I'm going to take that same signal and feed it into one of the inputs of an exclusive OR gate. Now I'm going to tie the other input down, so low. That turns this into a buffer. And then the output here becomes whatever it is I want to pass on to the rest of the control module. Now at the same time, I'm going to take the same signal right off here and feed it into the other input of this gate. I say the other end of this gate. I'm going to tie it to the next gate over. And then I'm going to tie the other end of that high. Tie the other input high. That turns this into an inverter. And coming out of this then is an inverted clock. Now, clock and inverted clock, since both signals come from the clock module, they're all tied together in the same node here. They should be exactly the same timing coming out of this exclusive OR, which means that when I look at it on the scope, I should have a uniform rise and drop at exactly the same time. Let me get this wired up real quick. Okay, so here are my two clock signals that are going to go out to the rest of the module here. This is a AT28C 256. This is a 32K EEPROM that I'm going to drop in here. And I'll have to pull up the pinouts for it so that I can get this wired up. But in the meantime, I want to go ahead and get power and ground. Those are in the traditional places here. Now I know that these two are address lines that we don't want to use. There's 8 address lines in a row here. 3 input-output lines, which are only going to use for output, plus 5 more up here. And then the rest of the control lines and address lines sit up here. And I will put a schematic up at the top of the screen for you to follow along as well. Pin 1 is address line 14, and I'm not going to use that today. Pin 2 is address line 12, and I'm not going to use that today. Pins 3, basically the rest of the pins here on the bottom I do have interest in, so I'm going to go back up here to the top. Pin 27 is write enable, that's active low. We want to pull that high because we don't want to be writing to the EEPROM, at least not in this situation. Pin 26 is address line 13. We're not going to use that, so I'm going to tie that low. Pin 25 is address line 8. I'm not going to use that, so I'll tie that low. Pin 24 is address line 9. We're not going to use that, so I'll tie that low. Pin 23 is address 11. Not going to use that, so we'll tie that low. And if you haven't figured it out, I'll put the instruction word right up here on the top as well, just as a reminder. I'm only using 8 bits as the lookup into this control. Bit 22, or sorry, pin 22 is output enable, and we want to be outputting, so I'm going to tie that low. I'm running out of pre-cut wires that are long enough. Let me make a few of these real quick. All right, let's see what we can do with this now. Pin 22 is output enable. We'll tie that low because we want to be outputting. Pin 21 is address line 10. We'll tie that low. We're not going to use that for the moment. Pin 20 is chip enable. Again, that's active low, and we'll tie that low because we want the chip to be enabled. This is a 74LS 138. This is a 3-to-1 line demultiplexer. And this is what I've done a lot of analysis on and reading of the data sheet in order to understand the timings and everything. And this one I'm going to use for the address bus 1 assert. So because it's an address bus 1 assert, it's going to be on all the time. It's not going to be triggered by the clock, which means that it's going to be a 45 nanosecond propagation delay from when the signals hit the inputs to when the outputs go, the output singular goes low. And because it outputs an active low signal, it's perfect for driving the line drivers, which require an active low signal. So I need to open this up for myself so I can see the pin diagram, and of course I'll put one up in the corner for you. A, B, and C, and I'm going to take the top 3 bits up. Actually, I'll take the bottom 3 bits down here. So A is pin 1, B is pin 2, and C is pin 3. And then my output enables 4, 5, and 6. 4 is low. And once again, this is always outputting. It's not triggered by a clock. It's for the entire cycle. So we want to make sure that we don't tie that to a clock. It's all the outputs are enabled. All of the enable pins are in their enabled state. So that's 5, and then 6 is active high. Now, pin 7, pin 7 here is output 7. Output 0 up here is one I'm going to use to drive my program counter to output onto address bus 1. The rest of those we'll just leave unconnected at this point. Let me get some wires made up for these. Okay, so I pulled these down this direction simply because I'm going to need to be able to take this EEPROM in and out regularly to reprogram it for a while. I do want to be able to get to it without having all the wires going over the top of it, at least not yet. And so that will leave then the 8 address lines that I will want to pull right here. We'll get to those in a second. Here is another 74LS 138. And again, I'll take care of power and ground real quick. And this one I'm going to use for the AND latch signal. Incorrect. Nope, I'm going to use that for the AND latch signal. I need to bring up my document here. Yes, that's going to be the AND latch signal. And I'm going to take these off the next 3 pins in order here. So this is going to be bit 2. So I've got 0, 1, 2, I'm sorry, bit 3, bit 4, and bit 5. And then I can take the clock and I can take this clock over here to one of the active low inputs, our active low enables. Now, in my drawing, I have an inverted clock, which would be high at the period of time that I want this to be asserted. I could use the inverted clock and put that into the active high signal, or I could use the uninverted clock and put it into one of the active low signals, and I chose to use the active low signal for no other reason than I've got two active lows and I may need to hang on to that active high for something else. I'm not quite certain yet. And then once again, I've got an output here. This is going to be the AND latch signal for this. Now is going to be the AND latch signal for the register. Finally, the last two signals that I'm going to take are going to come off the last two pins. And those two signals each are going to go through an AND gate. So this is going to be here. That's pin IO pin 6 and then IO pin 7. And those are both going to be ANDed. I'm looking at my diagram up here with the inverted clock. So I'm going to take this clock signal here and drop it up there, and then I'm going to also extend it from there over. Something is not aligned. You know, it is aligning right. And so my two outputs here are, let me just check my wiring, bit 0 and bit 1 for the AND latch, I'm sorry, for the load increment decrement. Now, we're not quite done yet because these two signals also need to be buffered. Because I don't have anything that is ANDing these together or any other condition that needs to take place, I need to run these through a buffer. So real quick, I'm going to take this output, put it into the LS86, which is then going to make some more wires here real quick. This needs to be buffered, so I'm going to take the other side of that low, and then this becomes the output. And again, this is the address bus 1 assert. This other signal is very similar. It needs to be buffered. So I'm going to take the signal from here, and then I need to tie that low as well. And I should have done this before I got these other wires in. There we go. And this is our new buffered output. This one is for the AND latch. So let me get these cleaned up a little bit. That then is the wire up for the control signals to control the program counter. Again, I have the assert to address bus 1 for the program counter. This would be some other register here. This would be a third register. This would be a fourth register, etc., all the way through. And the way I have this wired up, a value of 0 asserts the program counter out onto address bus 1. So that's very nice. This is the AND latch signal, and this has also gone through a demultiplexer, and output 0 is to latch the program counter. So once again, if I have 0 and 0, it means that my program counter is asserting to address bus 1 and latching at the end of the increment. Now the increment is not quite so straightforward. I have bit 6 and bit 7 here of the control byte are set to be the load, increment, and decrement for the program counter. Now increment is 01, so the low bit here needs to be a 0. The high bit here needs to be a 1, so that is something that's not going to be 0. But it will allow me to have all the control signals I need in order to execute a no-op instruction. So that's what we're going to take on next. I have to program this EEPROM, and so I have to write some code to program this EEPROM, so I need to pull that together. And then I've got my TommyPROM that I converted to PCB that I need to test, and so I'll be testing it with this to make sure that it's actually doing exactly what I need it to do. And then I need to rehook all of this back up to the register in the computer and make sure that it's actually counting correctly. I will program this such that every single instruction is equivalent to a no-op instruction. I did not put any LEDs on here to indicate exactly what's going on, and that's because I've got LEDs on the register itself for that, and I didn't want to add anything more to these signals. The LEDs on the actual register are buffered with a line driver, so that will make that a little bit more robust so I don't deal with power problems on the or LED draining power on the signal lines. So that'll be what's next, is I will take on getting this programmed, getting the code for this written, and I am going to be away from my desk for almost 2 weeks. And so I need something that I can work on other than breadboards, other than PCBs. The timing is good that I actually get to spend some time working on code, something other than the physical stuff. The next thing you'll see is going to be how we pull the code together, and I may end up spending some time working on the assembler. Thank you. We'll see you soon.